In this video, I will be discussing proportional share scheduling. So just as a recap, an OS scheduling policy will determine the two following things. One, the order in which a process is run, which indicates moving the process from the ready state to the running state. And two, the duration for which a process is run, which is moving a process from the running state back to the ready state after a certain amount of time. This could be due to input-output operations or just the need to run another process. But ultimately, the OS scheduling policy needs to decide how to run what processes and how long to run those processes for. Overall, the scheduler attempts to be as fair and efficient as possible, where fairness avoids the starvation problem, where a process never receives the CPU time it needs to finish its tasks, and efficiency aims to minimize the following three things. One, response time, which is how long a process waits to be run when it's in the ready state. Two, the turnaround time, which is the time it takes for a process to be completed. And three, the overall resource overhead. And those are just the resources used to run a process that we see, such as when we do context switching. And again, context switching refers to moving from one active process to the next. And it has a lot of high amount of resource overhead. So you need to minimize the amount of context switching that occurs in order to minimize that overhead. So just to recap some previously discussed scheduling policies. So first in, first out, that indicates that the first process that is ready will be run. Shortest job first, the process that requires the least amount of CPU time will be run. And then shortest time to completion first, which is very similar to shortest job first, but this introduces preemption. And if a shorter to completion process arrives after the current process is running, it may be interrupted in order to run that new process. So ultimately, you're always trying to run whatever is going to complete the fastest and potentially be interrupting processes. One thing to note is that shortest job first and shortest time to completion first are both not feasible or practical in the real world because we oftentimes or will never really know how long a process is expected to run. Round robin, all processes run for a predetermined time slice. And then lastly, the multi-level feedback queue, which introduces priority queues that run processes in higher priority queues first, and then processes in lower queues get promoted to higher queues over time. So what is proportional scheduling? So effectively, the policies that we've discussed previously strike a balance between efficiency and fairness and are thought of as general schedulers. Proportional scheduling, however, chiefly focuses on fairness and attempts to guarantee that every process will receive a certain percentage of CPU time. So in the case of lottery scheduling and stride scheduling, that CPU time granted will be proportional to the system resources that the process commands or requires. Whereas in the case of the Linux completely fair scheduler, that CPU time is evenly split amongst all active processes. And we'll get into those more over the next coming slides. So the main idea behind lottery scheduling is that you quite literally distribute lottery tickets and then hold a lottery to decide who wins. So each ready process receives a certain number of tickets that are proportionate to the size of the process and the number of resources it needs. And then a lottery is held at regular intervals to again pull those tickets to decide which processes get to run. The ticket numbers are drawn completely at random, and the process holding the selected ticket number will be run. Overall, due to the use of randomness, the share of CPU time granted should align with its share of system resources, but it's not always guaranteed, and we'll see that on the next slide. So say we have two processes, A and B. Overall, we have 100 total tickets. A receives 75 tickets, and B only receives 25 tickets. Now, because of this distribution, you expect A to receive 75% of the CPU time and then B to receive 25%. Overall, if you pick 20 numbers at random, this is a sample output of what could occur. If you go through and look at each of the numbers chosen, you'll see that A wins 16 out of the 20 times and B only wins 4 out of the 20 times. Now, of course, because these are randomly generated numbers, if you do this again, you'll likely have different results. But overall, it's not, you won't always have a perfect distribution of what should occur versus what does actually occur. And again, A should have won 75% of the time, but they actually won 80% of the time. But we do see that this proportion moves closer to 75% as more numbers are chosen. So just continuing on with that thought, with respect to the fairness of lottery scheduling, that refers to basically the percentage of time that a given process is allocated with respect to the percentage of system resources that it has. So in this instance, or in the previous example, I should say, a perfectly fair system would have had A winning 15 times and B winning 5 times, and we'd see a fairness value of 1. If you look at the chart to the right, that as the job length increases, that fairness value approaches 1. So that's just something to keep in mind with respect to lottery scheduling and some of the bias that we'll see depending on the job size. There are 3 different ticket mechanisms that enable just different approaches with respect to the lottery scheduling system. So ticket currency, users can allocate their tickets amongst their processes in a separate currency, and then those values are then converted to the global currency. So in this example, user A and user B both have 100 tickets each. A may convert their 100 tickets into 1,000 tickets in its own currency if it has its own distribution system by which it parses out those tickets. But when it comes time to actually do the lottery and check the ticket numbers, those 1,000 tickets are ultimately converted back into 100 total to ensure that the comparison between user A and user B is still even, and it's not as if user A just suddenly granted themselves a lot more tickets. Ticket transfer is the next mechanism, and that indicates that processes can hand off their tickets to other processes, which can lead to increased performance of critical processes. And then lastly, ticket inflation. Processes can temporarily raise or lower the number of tickets that it owns, which can signal the need for additional CPU time. Now, obviously, if you're in a greedy environment where all processes are just trying to maximize the amount of CPU time they have, this type of mechanism would not be good, because processes would obviously constantly be increasing the value of their tickets and capturing that CPU time. So it really should only be implemented if you're in an environment where processes will see that inflation happening and will respond in kind in order to grant the requesting process the additional CPU time that it may need. So lastly, one of the biggest advantages of lottery scheduling is that it's quite straightforward and simple to implement. So all you really need is a data structure to hold the process and ticket information, a random number generator to actually execute the lottery process, and then an indication of how many tickets are allocated and the total number of tickets that are allocated per process. So effectively, what you do is you would traverse the list of processes, and then you have a counter that basically checks what the boundary of a given process's ticket span is. So for example, if A is allocated 100 tickets and those are 0 to 99, its counter value will be 99. And then if the randomly chosen number is less than or equal to 99, then you've identified the winning process and you can move on. Alternatively, if it's higher than that number, then you need to check the next process to check that boundary condition. So ultimately, that's a suggested implementation of the lottery scheduling. Next, I will be introducing the stride scheduling. So this is somewhat similar in that we still have lottery tickets, but this scheduling policy seeks to correct the fairness problem and is considered a deterministic fair share scheduler. And again, the fairness problem was that because we're using random numbers in the lottery scheduling, the divvied out proportional CPU time isn't always perfect based off of the number of tickets allocated. So again, in stride scheduling, each process in the system will have a stride, which is inversely proportional to the number of tickets that it has. And anytime a process runs, you would increment a counter, which is called its pass value, with its stride value. And the process with the lowest pass value is chosen to be run next. And we'll see this example on the next slide. So say we have 3 processes and 800 total tickets to allocate. We give process A 100 tickets, B 50 tickets, and then C 250 tickets. Then to calculate the stride value, we pick an arbitrarily high number, 1,000 in this case, and divide that by the ticket value allocations. So now A's stride value is 100, B's is 200, and C's is 40. Now, if we think about this and we remember how stride scheduling works, where you're incrementing the pass value by the stride value, because C has a much smaller stride value relative to the other processes, we should expect to see that we'll run C much more frequently than A or B. And this makes sense because C is allocated quite a bit more tickets compared to the other processes. And if we do the math here, again, if we have 800 total tickets, we expect A to be run twice or chosen twice, B once, and then C 5 times. And then if we look to the right, we can see a sample execution of this. So at first, all processes have the same pass value of 0. We'll say we start off with running A, now just B and C have 0. So then we'll run B, and now C has 0. But again, the pass values for A and B are updated by the stride values. So A's pass value is 100 and B's is 200. And because C's is only 40, that means we get to run C 3 times in a row because it's still going to have the lowest overall pass value. Then C's pass value exceeds that of A, so we run A again, and then we're back to running C until all are even at 200, and then this cycle completes again. Now, if we count up how many times each respective process won, it's exactly perfect for what we said initially. We'll see A wins twice, B wins once, and C wins 5 times. So overall, the proportions of CPU time received are perfect based on the number of lottery tickets it has. So again, similar to the overall lottery scheduling, but this one just completely eliminates that fairness problem. Next, I'm going to talk about the Linux Completely Fair Share Scheduler. So overall, this scheduling policy is not concerned with allocating processes based on share of system resources. This is actually concerned with ensuring all processes receive the same amount of CPU time, but its big focus is seeking to minimize the overall time spent making scheduling decisions. Now, this is super critical because even in highly optimized systems, scheduling uses or can use about 5% of overall CPU time. And obviously, if you're not in an optimized system, that number will be greater. And ultimately, you want to really minimize that overhead. You would rather your CPU actually be executing processes than spending time deciding which process to run. So again, this scheduler just seeks to make that as simple as possible. So what it does is it fairly divides the CPU time by keeping track of how much CPU time a given process has received, and that's reflected by the virtual runtime. So it's somewhat similar to stride scheduling in that if we remember from stride scheduling, we choose the process that has the lowest overall pass value in terms of choosing which one to run next. And this is just choosing which one has the lowest overall virtual runtime. And every time a scheduling decision is needed, it just literally runs whatever has the lowest V runtime, and overall tries to ensure that all processes receive the same amount of runtime. So ultimately, the Linux CFS has 2 parameters that ensure fairness and minimize inefficiency by minimizing the overhead of context switches. So the first parameter is schedule latency, and this value determines how long a given process should run before a context switch is considered. The latency value is divided by the number of viable processes, and the result is how long a process can run for. So say you have a scheduled latency value of 48 milliseconds and 4 active processes. You would just divide 48 by 4 and find that each process can run for 12 milliseconds before a context switch is considered. However, where we get into trouble with this is if you have a lot of active processes, say you have 48 active processes, this value alone would indicate that every process runs for just 1 millisecond each, which would lead to a whole lot of context switches and just really tanks the efficiency. So this is where the minimum granularity comes into play. This value determines the minimum time slice a given process should run for, regardless of the latency calculation above. So if, say, you set it to 6 milliseconds, then even if we have 48 active processes and the scheduled latency value is 48, each process would still run for 6 milliseconds instead of 1 millisecond. And again, this is to ensure that you're not executing context switches too frequently. Another unique feature of this scheduling policy is that it offers the ability to prioritize across different processes. So a nice parameter is used to indicate priority. Positive nice values indicate lower priority, whereas negative nice values indicate higher priority. And if a process is granted a higher priority, it receives a larger time slice to run, and its vRun time accumulates at a lower rate. So not only does it get to run for longer, but it also, in theory, should get to run more frequently because its vRun time is not being accumulated as quickly with respect to other processes. And again, all the Linux CFS scheduling policy seeks to do is, or not seeks to do, but the way it makes its scheduling decisions is just by picking whoever has the lowest overall vRun time. Now, continuing this thought of overall, being focused on efficiency, the data structure that's used is a red-black tree because it offers quick deletion and insertion of processes and offers quick identification of the process with the lowest vRun time. And one thing to note is that this data structure only includes the processes that are in the ready state to minimize its size. And so the ability to quickly delete and insert processes is critical for this data structure because obviously we know processes move from ready to potentially block states, quite frequently depending on what it's trying to do. So overall, all 3 scheduling policies strive to ensure fairness in different ways. Lottery scheduling uses randomness to partition out the CPU time. Stride scheduling deterministically assigns fair CPU time. And then the Linux completely fair scheduler monitors the CPU time a given process is utilized and runs processes that have consumed the least amount of CPU time. This policy also attempts to minimize time spent making scheduling decisions. Overall, proportional share scheduling policies require ticket and priority assignment, which introduces challenges that previous scheduling policies do not have. So something to just keep in mind of when you would try to use these scheduling policies instead of the previously discussed scheduling policies. And it really depends on the specific requirements of your system. Lastly, these are the resources that I used. Thank you for watching.